about new things. The previous chapter is about the circular motion. That chapter will be so much related to this new chapter that we are going to study, which is the gravitational fields. We are going to use some of the rules from the circular motion and also the formula to be applied to the gravitational fields chapter. A gravitational field is a region around one mass which affects on the nearby masses. It is very weak, however, which is why the effect is only significant on large objects like the Earth. We can represent the Earth's gravitational field by drawing field lines, showing the direction of the gravitational force on masses in the field. In this case, field is radial and equally spread around the Earth. On the surface of the Earth, the gravitational field is approximately uniform because the field lines are virtually pointing in the same direction and are equally spaced. This is why we assume the acceleration due to gravity is a constant of 9.81 meters per second squared. Because the change at small vertical heights is negligible, Newton's law of gravitational states that all masses attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between the center of the mass. This gives us the equations F equal to minus g times m over r squared, where g is the universal gravitational constant of 6.67 times 10 to the power of the minus 11. Capital M is the mass of the larger body and small letter m is the mass of the smaller body. And r is the distance between the centers of the mass of the two bodies. The minus sign simply refers to the fact that the force is attractive. For example, two bodies, one of mass 6 kilograms and the other of mass 20 kilograms, are placed 50 centimeters apart. From these, we can work out that the gravitational force acting on object is 3.20 times 10 to the minus of 8 newtons. The force acting on each body is equal because they are attracted to each other. The gravitational field strength is the force per unit mass at a point in a gravitational field. For a uniform field, the equation is G equals F over m, where F is the force experienced by the body and m is the mass of the body for a radial field. The gravitational field strength obeys an inverse square law. The equation for it is G equals gm over r squared. You can see how the gravitational field strength would decrease the further you are from the center of the body producing the field. This formula can be used to work out the masses of celestial bodies. For example, given that the gravitational strength on the Earth's surface is 9.81 newtons per kilogram, and then the radius of the Earth is around 6,400 kilometers, we can work out the mass of the Earth to be 6.02 times 10 to the power of 24 kilograms. When considering planetary motion, the gravitational force acting on the body orbiting is equal to the centripetal force because the force acts perpendicular to the direction motion by equating the two formulas and using the formula for the speed of an object in circular motion, we get the equation t squared equals to 4 pi squared over gm r cubed, where t is the orbital period in second and r is the distance between the centers of the mass orbiting the body and the body being orbited. This equation shows Kepler's third law, which states that t squared is directly proportional to r cubed. This also suggests that for a set of celestial body, the planets of our solar system orbiting the same large body, each of the sun t squared over r cubed is constant and is equal for all the celestial bodies. For example, given that it takes 365 days for the Earth to orbit the Sun, and the distance of the Earth from the center of the Sun is 1.5 times 10 to the power of 11 meters, we can work out the mass of the Sun to be about 2 times 10 to the power of 30 kilograms. Given that the orbital period of Mars is 687 Earth days, we can use the Earth orbital characteristic to work out how far Mars is from the Sun, as being 2.29 times 10 to the power of 11 meters. A geostationary orbit is an orbit around the Earth whose orbital period is 24 hours. They are located above the equator and are always practically above the same point on the surface of the Earth. This makes them useful for TV satellites because the dishes can be pointed to a fixed point in the sky, which is quite convenient. Okay guys, that is the introduction to our new chapter of gravitational fields. I do hope you understand what I'm saying in this video. We will discuss more about this topic in our Zoom session and also session in WhatsApp. Okay, thank you for attention and bye-bye.